Today we are going to look at the idea of moment of inertia. We know that inertia is a body's resistance to change in motion. For moment of inertia, we're looking for a very similar situation, only now, just like we've been dealing with, instead of translational or linear motion, we're talking about rotational motion. The symbol for moment of inertia is a capital I. Then we have the sum, which we're getting pretty familiar with this sigma, right, of all of the individual particle masses times the radius around the axis of rotation squared. The units for our moment of inertia, since we have mass and radius squared, are going to be, mass will be in our normal kilograms, and then radius would be in meters squared. So we have kilogram meters squared. Let's take a look at an example. In an effort to be the star of the halftime show, a majorette twirls an unusual baton made of 4 balls, each of mass 0.25 kilograms, fastened to the ends of very light rods. Each rod is 1 meter long. Find the moment of inertia about an axis perpendicular to the page and passing through the point where the rods cross as shown. So I made a little model, which is why you get to see me today. This is my little model. The model that we have doesn't look quite like our image because I have to use a little magnet in the center, but this is essentially what's happening. It's rotating about the central axis, and all 4 of the particles on the edges are spinning. Okay, so that means we have 4 particles, which means we have to sum up 4 components. Looking at the information that we have, we know that all masses are 0.25 kilograms, and we know that all R values, or radii, are 1.0 meters. In our EMS, we know that our moment of inertia is going to be equal to the sum of all of the individual masses times the radius of each individual mass squared. For M, we would want to actually write out all of the individual components. Since we have 4 values, that's mass 1 R1 squared plus mass 2 R2 squared plus mass 3 R3 squared plus mass 4 R4 squared. But we also want to remember that all masses are the same and all radius are the same. Because of that, we can simplify our equation to be 4 times the mass of the object times the radius squared. Then I can finally substitute in, and I get my moment of inertia is equal to 4 times the mass, which was 0.25 kilograms, times the radius, which was 1.0 meters squared, and that gives me 1.0 kilogram meters squared for my moment of inertia. Our second example requires that we look at a slightly different situation. The majorette tries spinning her strange baton about the axis OO as shown. Calculate the moment of inertia of the baton about this axis. So this one's a little bit different. Rather than rotating perpendicular to the page, now it's just spinning in a circle. So really the top and the bottom particles aren't really moving. It's only the middle 2 particles that are spinning, which changes the behavior of our moment of inertia. Our E is going to be the exact same. So moment of inertia equals the sum of the masses times the radius squared. Our M, if I label these, I can call them 1, 2, 3, and 4. What's important is I recognize that particle 1 and particle 3 really aren't part of the system at this point because they're not moving. So my moment of inertia in this case is just going to be mass 2 radius 2 squared plus mass 4 radius 4 squared. And again, my masses are all equal and my radii are all equal. So I can simplify this to moment of inertia is equal to 2 mass times the radius squared. And my substitution will give me a moment of inertia of 2 times 0.25 kilograms times 1.0 meters squared. And I end up with a moment of inertia this time that's half the size of the other one, 0.5 kilogram meters squared. As we move to the next page, I'm going to really recommend that you watch the Flipping Physics video on moments of inertia of rigid objects with shape, because these are a little bit trickier. One of the things that you're going to learn in that video is the idea that moment of inertia, if you have a rigid object, a solid object, is made up of a whole bunch of point masses. Like we had 4 points that were attached by rods around the axis of rotation in the middle. But if we have a rigid object, a solid object, what we're really getting is a whole bunch of individual little point masses that all add up to equate to one larger mass. So each of these little dots that I draw, there would really be no space between them. It would really be each individual little point mass was connected to the next or right next to the previous one until you had a solid component. Multiple point masses are added to get the total mass m that we're going to use for these rigid objects. The moment of inertia is equal to that total mass times the radius around the axis of rotation squared. Each of the equations on the right side of the page use this moment of inertia of a hoop as a foundation. There are a few of these that are probably worth committing to memory, and that would be the annular cylinder or ring about a cylindrical axis, the solid cylinder or disc about a central diameter, the hoop of any diameter, and the slab about perpendicular axis through the center. Before we call it a day, let's look at an example where we're connecting moment of inertia and torque. An object is supported by a horizontal frictionless table and is attached to a pivot point by a cord that supplies centripetal force. A force F is applied to the object perpendicular to the radius, causing it to accelerate about the pivot point. The force is perpendicular to R. What's the moment of inertia of the object and torque about the pivot point? What's the object's angular acceleration? If we take a look at our object moving, we have a little puck, and so it's essentially a little frictionless item moving around the table. Here's our radius. Our force is being applied at a 90-degree angle, so we know that we're talking about our sine theta is 90 degrees. The first thing it asks us to find is the moment of inertia. So our equation for moment of inertia we know is capital I is equal to the mass times the radius squared, and that's already solved for moment of inertia, so we're good on that one. The next one it's asking us to find is torque, and the equation for torque is our torque is equal to R force sine theta, but we know in this case that sine theta is sine of 90, which is 1, so our equation for torque is going to be R times the force. Finally, it asks us to solve for angular acceleration, and our equation for angular acceleration, the linear version, remember, is F equals ma, but the rotational version is torque is equal to mass times angular acceleration. So this one we do have to rearrange to solve for angular acceleration is going to be the torque divided by the mass. And then we can also plug this in here to go one step further. The angular acceleration is equal to the radius times the force divided by the mass. Don't forget to go watch the Flipping Physics video of moments of inertia for rigid objects with shapes. That's definitely going to be helpful before we take the next step. You should also now be able to answer problem bank question number 10 with no difficulty.